Hey. Good morning. Yay, we're going to talk about titrations. This is something that my students missed last year due to the pandemic. Don't want to bring that up. So titrations are great. You're going to see the word titrations a lot, especially when we get to the end of this year, not semester, but year. We talk about acids and bases. Okay, so let's take a look at titrations. I should have imported some pictures, but I didn't. That means I get to draw. Yay. All right, titrations. Titration is something that you do in the lab. All right, a titration is a process. It is typically a process used for many reasons. All right. And one, often to determine the amount of a chemical species present. All right. So a titration involves a burette. All right. So we would set up your burette. I don't know that we've talked about burettes yet. Kind of looks like this. Well, we have very small markings. It reads from 0 to 50, right? So it reads upside down. There's a little, it's called a stopcock right here. You open it and close it, and a little bit can come out at a time. And we would put typically a flask down here, an Erlenmeyer Flask. I'm going to see if I can make that better. Oh yeah, that's looking good so far. Oh, it's all right. I never do too good. This would be our Erlenmeyer Flask. Okay. It's always nice to put a white piece of paper underneath it. In this flask, we would have our analyte. That is what we are analyzing. Right, what we are trying to determine the amount of a chemical species in, all right? And here we would put our titrant, okay? All right. This is often used in acids and bases. It is used in redox equations, which we'll get to. We're going to go ahead and look at it in terms of acids and bases, all right? So what happens is our titrant is of known concentration, right? It has often been standardized. Okay, and what that means is it was a solution that was made and then had the concentration tested through a titration to determine its exact concentration. Okay, so we would put a standard solution in there. And you would do that before, right? So you can have several titrations going on, titration after titration after titration. Okay, so in here, I have a solution of known concentration, and I will use a very particular volume of that solution to cause a reaction with this solution here, okay? What's important to know here is must know the volume, right, of substance present. What we're often trying to determine, usually trying to determine the concentration, or more specific, usually trying to determine the number of moles of substance present, okay? And what you'll have is you'll use a net ionic equation, and this can be easy, but it's important that you understand. A net ionic equation can be used to determine the stoichiometry of the reaction. And the reaction always involves something in the titrant, a titrant species reacting with a analyte, that would be an analyte species, to produce a final product. All right. Now, if the titrant species is an acid, particularly a strong acid, and this is a base, particularly a strong base, then our final product will be water. All right. If this is a strong base, and this is a strong acid, then the final product will be water. Okay. And it often is. I think for right now, it probably will be. All right. Sorry, there's a hair on there. Let me think of what else I might need to tell you. Oh, if that is the case, then the net ionic equation will be this, right? Or it will be this, which is is the same thing. And if you're thinking, well, does it matter how I write it? Absolutely not. It does not matter. Okay. It doesn't matter who's first, who's second, but that if in fact you have a strong acid, strong base, or strong base, strong acid titration, then this will be your net ionic equation. Doesn't matter what order you write it. Okay. So let's look at an example. Shoot, I should have put some examples on here. Let's say that it takes 22.50 milliliters of 0.998 molar NaOH to neutralize 25.0 milliliters of HCl. What is the concentration of HCl? All right. Okay. This will probably be the only example we do here for now. All right. Oh, I'm just thinking of some other things I need to talk about. Okay. Well, in here is my titrant. Once again, this will be my 22.50 milliliters of my 0.998 molar sodium hydroxide. And remember, the major species there is the hydroxide. All right. This burette would read upside down. Sometimes I've seen questions where a student is given, you've seen them already, I think, a reading on a burette. Let's say that's 10, that's 20, that's 30, right? And you actually have to read it. So this would be 20. This would be 25. So this would be 24, 23, 22. So we would be right around here, right? It would kind of be sitting right there. So this here is the volume. this would probably read to the tenths place, and your recording of it, therefore, should go to the hundredths place. Okay, you need to recall that. And they'll ask you, what is that volume? And first of all, you need to understand how to read it backwards. And you need to make sure you go one place past what is for certain, all right? That's why I wrote 22.50 and not 22.5. All right, so that's where we are here. All right, it's a closer up look of what's going on there. Down here, once again, we have our analyte, not so pretty. This is our HCl, and we have an exact 25.0 milliliters of it. What happens? Oh, we also place an indicator. We need to place an indicator because right now, everything is clear. Our acid is a clear solution. Our base is a clear solution, right? So it's going to appear as though nothing is happening. So I'm going to put phenolphthalein. I'm going to use phenolphthalein because it's the perfect indicator when we have a strong situation, strong acid, strong base. So this is going to change colors around that equivalence point. Now, phenolphthalein is, phenolphthalein is clear in acidic solutions, and it is pink in basic solutions. So what I have in my titration is in here, right? I have a bunch of hydrogen ions, okay? I have a bunch of hydrogen ions because, guys, this is a strong acid. And even though we haven't talked about it yet, that means it dissociates completely. Maybe I should have started somewhere else, huh? Dissociates completely. So, and it is the hydrogen part that is the acid part. Remember, we said that our reaction will be hydrogen and hydroxide making water, okay? So in fact, this is, we don't have to take too much longer, but we just need to understand, right? Aqueous, H2O liquid plus NaCl, aqueous. And you can see, hopefully, that the sodiums will be spectators, the chlorides will be spectators, and what's happening is this from the acid is reacting with the hydroxide from the base to make water in a 1-to-1 ratio, all right? Such that in here, I have my hydroxides, full of hydroxides. Yes, the sodium is in there too, but it's not doing anything. And in here, I have my hydrogens, right? So every hydrogen, or every hydroxide I add will grab a hydrogen and make a water, right? So I need to continue to add this to this so that every hydrogen is removed by one of the hydroxides, right? And once every hydrogen has been removed, I no longer have any hydrogen. I have created water. The acid has been neutralized by the base. This is a neutralization reaction. It's an acid-base neutralization reaction, okay? So that I put the indicator in there because once I have one itty bitty excess of base, it's going to change colors. It's going to change colors. And I'm going to stop. Okay? So my end point is the point at which the color changes. So I will stop my titration. Throughout that entire time of adding, you're swirling it around. Swirling it around. Make sure it's mixing up. And you'll see it's turn pink, and you'll swirl the pink out. It'll turn pink, you'll swirl it out. Either I'll be back in the classroom, so I'll be able to video that or show it to you in the classroom one way or the other. Okay, the equivalence point is not the end point. The equivalence point is the stoichiometric point, or the point at which all analyte has reacted and none remains, right? That perfect point. You need the color change to occur at the equivalence point. And if we have a strong acid, strong base reaction, phenolphthalein is a good indicator for that. Okay? So now let's go back to our reaction. It takes 22.50 milliliters of 0.998 molar and 25 milliliters. Okay, I'm going to remember that. 22.50 milliliters hydroxide. That was 0.998 molar hydroxide to react with 25.0 milliliters HCl, question mark, concentration. Concentration equals moles HCl over liters solution. We know the liters. It is the 25.0 milliliters divided by 1 over 1,000. Right, divided by 1,000, divided by 1,000, divided by 1,000. What am I doing? Divided by 1,000. Divided by 1,000. And that's liters per milliliters per liter. Okay, whatever. Ugh. So anyway, we know that we need the moles of HCl. That was ugly. And we needed it to be divided by 0.0250 liters of the solution. So this right here is what we're going to look for. Super simple, because we know that, and this is our net ionic equation. I made this way too long, but I didn't. I needed you to understand the titration. So I know that 22.50 milliliters, 1,000 milliliters, 1 liter. According to molarity, 1 liter is 0.998 moles. Moles of what? Moles of hydroxide. We know that every 1 mole of hydroxide reacts with 1 mole of hydrogen ions, and that there is 1 mole of hydrogen ions and every 1 mole of HCl, right? That just shows everything. Thus, we have on 0.0225 times 0.998 equals 2.25 times 10 to the negative second moles of HCl divided by the 0.0250 liters divided by 0.025 equals 0.898 molar HCl. All right, there are questions that can be asked about this. What if this, what if that? It's really important that you really understand the titration part of titrations. And then you can do the math. The math is easy. It's all easy. But it wasn't when I was a young kid, but I didn't have such a good teacher. Anyway, I'm gonna end this, stop share, and I think I'm gonna be done making videos today. It's now 11:15. It was 10 last time I looked. end. Have a great day.